Welcome to Module 2 of this video series, where we will be exploring the world of biomass fuels. This is one of the most critical parts of our training series. In real biomass plants, fuel variability is our biggest daily operational challenge. We are going to explore the chemistry, types, storage, and safety practices of biomass so that you can run your boiler room with ultimate stability, efficiency, and safety. To begin simply, biomass is organic material that acts as a solar battery. Through photosynthesis, represented by this classic equation, plants consume carbon dioxide and water to lock up sunlight as carbon compounds. When we burn biomass inside a boiler, we are breaking those carbon bonds to release that heat. However, a boiler doesn't just burn pure carbon. It has to process moisture, ash, and volatile gases all at once. Let's look at the primary biomass fuels commonly utilized in field operations, focusing on how their distinct physical traits impact boiler performance. While each option presents unique advantages in availability or cost, they also introduce specific technical challenges, ranging from combustion volatility to equipment wear. Understanding these critical trade-offs is essential for optimizing our combustion strategy and safeguarding system longevity. Wood chips are relatively stable combustion with high heat value. However, they struggle with high seasonal moisture variation and bark contamination. Tree branches also normally come with it and eventually interfere with the smooth running of hopper, conveyors, and bunker. Moisture could go more than 40% during the rainy season. It could be mixed with PKS or cashew cake to further increase the heating value. Next is sawdust. Sawdust is highly reactive and exhibits extremely fast ignition due to its expansive surface area. However, this fine particle size presents massive dust explosion risks, particularly within enclosed feeding and handling systems, where airborne dust can easily find an ignition source. Consequently, safely utilizing this fuel requires stringent dust mitigation protocols, specialized ventilation, and robust spark detection systems to prevent catastrophic flare-ups. Here we have palm kernel shells, or PKS, often utilized for their specific burning properties in industrial applications. If used 100%, it generates high furnace temperatures, leading to grate and refractory issues, and contributes to black smoke emissions if settings were not properly balanced. Mixing 25–30% of it to wood chips produces economical results. This photo was taken when using 100% PKS. When combustion is not optimized, you may see signs like heavy black smoke, indicating incomplete burning or improper fuel usage. Rice husk is highly abundant and dry, but packed with abrasive silica ash. This unique composition causes extensive tube wear, fouling, and demanding soot blower cycles that can rapidly degrade boiler efficiency and compromise component integrity. Consequently, successfully utilizing this low-cost fuel requires heavy-duty, erosion-resistant materials and strict ash management protocols to counter its intense mechanical wear. Cashew shells are also used as a fuel source, though they require careful management. Raw cashew shells contain 15–35% oily CNSL, or cashew nut shell liquid. While high in energy, CNSL vaporizes violently, creating massive black smoke, toxic VOC emissions, and acid corrosion. This is cashew cake, a byproduct that serves as a processed fuel alternative. Cashew shell cake, or De-Oiled Cashew Shell Cake, DOC, is the solid residue left after oil extraction. This is the more stable form, yielding 4,500 to 6,000 kilocalories per kilogram with very low smoke. But the experience of some mills says otherwise. When 30% is mixed with wood chips, it generates big clinkers, rapidly corrodes metal parts in the furnace, and shortens the life of flue gas filter bags. This is how 30% DOC mixed with 70% wood chips affects the grate elements inside the furnace after less than a year of usage. You can see how rapidly it corrodes and punctures the step grates. The sideware plates are easily eaten as well, and eventually exposing the cooling air ducts, which are not as resistant to extreme temperatures as the grate elements. These are the clinkers that developed when using 30% DOC. These clinkers form when the inorganic minerals inherently found in biomass fuel, such as silica, potassium, and sodium, are subjected to combustion temperatures that exceed their relatively low ash melting point. This causes the ash to liquefy into a sticky, molten slag that drips down toward the cooler grate. As this liquid slag comes into contact with the cooler air and metal at the grate level, it solidifies, fusing together with surrounding unburned fuel, sand, and loose ash into dense, stony masses. On the same run, these are the things which dropped inside the ash bin, more clinkers than ash. If you asked any boiler operator what their biggest operational headache is, they will say moisture. According to thermodynamic physical law, Q equals ml, water inside the fuel must consume vast amounts of latent heat just to vaporize before carbon ignition can start. Wet fuel instantly drops furnace temperatures, produces heavy black smoke, and forces the steam pressure to plummet. We must look at fuel with dual lenses: calorific value, which tells us how hot it can burn, and ash content, which tells us how dirty it is. Look at this image. That is a boiler tube covered in molten ash clinkers and slag. This ash insulates the steel tubes, ruins heat transfer efficiency, drives up stack temperatures, and can trigger emergency manual shutdowns. Let's talk about the overfeeding trap, the classic beginner operator mistake. Wet fuel arrives, steam pressure drops, and the operator dumps more fuel into the grate. But that extra wet fuel just smothers the flame. 10 minutes later, the huge wet pile finally dries out and ignites like a bomb, driving steam pressure and temperatures dangerously high. You must learn to wait, let the fuel dry, and balance draft air. This database maps out the engineering parameters of standard global biomasses. Notice that for highly challenging fuels, like rice husk, we recommend fluidized bed boilers. The intense thermal mass and turbulent mixing of a fluidized bed can handle inconsistent fuels, whereas grates will quickly foul up or suffer clinker damage under high ash loads. Now, let's tackle the common issues encountered in storing biomass fuels. Fuel management starts long before fuel reaches the furnace. In biomass yards, pile management is a major safety concern. Deep inside huge stockpiles, natural bacterial action generates chemical heat. Without proper ventilation and height limits, this heat builds up until the pile spontaneously combusts. You must run a strict first-in, first-out system and actively monitor internal pile heat. Safety is non-negotiable. Biomass dust is highly combustible. If dust is suspended inside an enclosed conveyor or silo and meets an ignition source, such as static electricity or a friction-heated bearing, it will detonate. Always keep conveyor galleries thoroughly vacuumed, maintain active pull cords, and never weld near fuel yards without a validated permit and fire watch. Palm Kernel Shells, PKS, mushroom sprouts. After a few weeks of storage, a section of the outdoor PKS pile begins to look like a forest floor. Clusters of small mushrooms and a white, thread-like web, mycelium, are visibly spreading across the surface of the shells. The why behind it. PKS naturally contains residual palm oil and moisture. When exposed to rain or high humidity, it becomes the ultimate gourmet substrate for fungi. While mushrooms might look harmless, fungal growth means dry matter loss. The fungi are literally eating your fuel, which directly degrades the net calorific value, heating efficiency, of the PKS. Wood chips, visible fumes, and spider infestations. A light, hazy mist hangs over the indoor wood chip pile, accompanied by a sweet, pungent, or musty odor. If you dig a few inches into the pile, the material is noticeably hot to the touch. Meanwhile, the perimeter and surface of the pile are laced with heavy cobwebs, and a disturbing number of spiders are thriving in the area. The why behind it. Fumes. This isn't smoke, yet, but rather water vapor and volatile organic compounds, VOCs, pushed out by microbial self-heating. How moisture wood chips ferment, creating internal temperatures that can easily exceed 60 degrees Celsius, 140 degrees Fahrenheit. How about the spiders? The warm, humid microclimate of a self-heating woodpile is an open invitation for insects. Spiders move in as the apex predators of this tiny ecosystem, thriving on the abundance of fungus gnats, beetles, and mites attracted to the decomposing wood. Rice husks, the multi-issue dilemma. Handling the rice husks creates a massive, choking cloud of fine dust that settles on every flat surface in the facility. Despite the massive physical volume of the pile, it feels incredibly light, and any slight breeze sends your inventory flying away. The why behind it. Rice husks suffer from three major storage and handling headaches. Extremely low bulk density. They take up massive amounts of physical space relative to their energy output, making logistics expensive. High silica and dust. The dust is highly abrasive, wearing down mechanical conveyors and causing respiratory risks for workers. Explosion risk. Because the dust suspended in the air is highly combustible, a single spark in the storage area can trigger a dust explosion. The black pile, liquid leaching. A dark, viscous, and sticky, oily substance is pooling at the base of the cashew nutshell pile. It's slowly corroding the concrete floor, leaving pitted marks and giving off an acrid, irritating chemical smell. This liquid is cashew nutshell liquid, CNSL. When cashew shells are piled high, the physical weight, compaction, combined with ambient heat, squeezes this natural oil out. CNSL contains anacardic acids, making it highly caustic and corrosive to both concrete and metal handling equipment. It's also an environmental hazard if it reaches local waterways. Other common biomass storage issues. If you are managing a biomass yard, you will inevitably run into these hidden culprits. Spontaneous combustion, self-heating. The issue? The ultimate nightmare of biomass storage. How it happens? In large, compacted piles, especially wood chips, bark, or bagasse with greater than 30% moisture, microbial activity generates heat. Once the pile passes 50 degrees Celsius, chemical oxidation takes over, driving temperatures up to the ignition point deep within the pile, without any external spark. Bridging and rat holing, silo flow failures. The issue? You open the bottom discharge valve of a silo, but nothing comes out, even though the silo is full. How it happens? Biomass particles are rarely perfectly uniform. They are fibrous, irregular, and interlocking. Bridging occurs when particles lock together to form an arch over the discharge outlet. Rat holing occurs when only a narrow funnel of material directly above the outlet flows out, leaving the rest caked to the silo walls. Moisture reabsorption and pellet disintegration. The issue: premium wood pellets turn right back into a useless pile of sawdust. How it happens? Manufactured biomass like pellets or briquettes are highly hydrophilic, water-loving. If stored in humid environments without proper ventilation or sealing, they absorb ambient moisture, swell, lose their structural integrity, and crumble. Dry matter loss, energy degradation. The issue: you store 1,000 tons of biomass, but when you go to burn it months later, it feels lighter and produces significantly less energy per ton. How it happens? Even if a pile doesn't catch fire or grow visible mushrooms, microscopic bacteria and molds are constantly consuming the easily degradable carbohydrates in the biomass, slowly leaking your energy profit into the atmosphere as carbon dioxide. Now, let's go back to the heating values of different fuels and make a comparison. Our top bar shows cashew shell cake leading with up to 19.5 megajoules per kilogram, followed by PKS and eucalyptus. Look at the bottom bars. Wet wood chips and bagasse drop down to 8 or 10 megajoules per kilogram because of their high moisture. This proves why pre-drying fuel or purchasing higher quality cake can drastically reduce the total volume of fuel you need to feed. In reality, successful biomass operation is about intelligent mixing. We mix fuels to balance price and stability. During the rainy season, you might mix wet bagasse with wood chips and dense PKS to act as a combustion booster. Always remember, buying dirt-cheap, poor-quality fuel might seem smart on paper, but if it causes boiler shutdowns, it will cost your company much more in lost steam production. To wrap up Module 2, always remember these 3 engineering principles. First, boiler controllers prefer predictable fuel over perfect fuel. Second, plant safety relies entirely on dry dust hygiene and pile monitoring. And third, biomass is only renewable and clean if we run highly efficient, smokeless combustion. Thank you for your focus. We have now completed our look at biomass fuels. In the next module, we will shift our focus to the mechanics and operation of water tube biomass boilers. Thanks for watching.